Yeah, next we have Zhi Wang presenting on regret bounds for meta Bayesian optimization with an unknown Gaussian process prior.
Thanks for the introduction. This is joint work with Baumjunkin and our advisor, Leslie Cabling. So again, as a recap, Bayesian optimization is a popular global optimization approach when we have functions that are expensive to evaluate, and we only have access to potentially noisy evaluations of the function. Problems like this appear in many different areas. For example, action selection in robotics, hyperparameter tuning in machine learning, and so on. So a typical paradigm of Bayesian optimization is to model the function f with a Gaussian process prior, and then it sequentially choose the new query point, evaluate its function value, and update the model to be the posterior so that in the next iteration, the data collection strategy can be more informed. But in practice, we don't really have the full knowledge of what such a prior is. And a common workaround is to re-estimate the prior parameters once we collect more data on the function f. However, this introduces a Bayesian optimization version of the chicken and egg problem. So our prior model selection depends on the data that's been collected, and the data collection strategy depends on having the correct prior. Partly because of this, very little theoretical evidence can be shown when we don't have a known Gaussian process prior. In this work, we're going to break this circular dependency by instead letting the prior depend on some past experience with similar functions. So that means we're going to use them as the meta-training data, which means functions that are sampled from the same prior as the function f. Our approach can be viewed as a version of meta-training for Bayesian optimization, and it simply works in two phases. In the offline phase, we're going to collect those meta-training functions, which means functions that are sampled from the same prior. We use those data to estimate the prior, and in the online phase, we are given a new test function to optimize. We take the prior to model such a function, and once we have more observations, we construct unbiased estimators for the posterior and use them in a variant of the GPUCB approach. So here's how it proceeds. Basically, it chooses the input that has the highest upper confidence bound to evaluate in every iteration. One thing to notice is that our estimations of the posterior variance and the UCB coefficient both depend on the number of meta-training functions. So roughly speaking, those parameters are set in a way to compensate our uncertainty about our estimation. And the more meta-training functions we see in the offline phase, the more confident we are about our predictions. One nice thing about using these setups of the parameters is that we can derive a regret bound for meta Bayesian optimization, even if the Gaussian process prior is unknown. So here we show a version of the regret bound for the simple case where there's finite inputs and the underlying ground truth kernel is linear. In this case, the regret bound we care about is the simple regret, which is defined as the difference between the best function value and the function value of the best observation. Under the assumptions that our meta-training functions are indeed sampled from the same prior, and that we have enough number of those meta-training functions, we can show that if we have t number of observations on the test function, with high probability, the simple regret can be bounded by this expression with two multiplicative terms. The first term decreases to a constant as the difference between n and t increases, and the second term decreases to standard deviation of the observation noise as the number of observation t increases. For more general results, please come to our poster. Empirically, we verified our experiment. We verified our approach in robotics tests. And I'll see you at the poster. Thank you.